Alright, hey everyone. Aim of this video is to understand the fundamental theorem of calculus, and in particular to find out where it comes from. So here it is, basically, the fundamental theorem of calculus, and it's just the thing that tells you what an integral is. It tells you that the integral is actually the area between a curve, the curve of, in this case, f of x here, between the bounds a and b. So wherever that may be, it tells you that the area is the antiderivative at the point b, take away the antiderivative at point a. That's basically all it says. So if we have a look over to this little graph over here, let's say that this line has the equation f of x. And let's just define some random points. Let's say that this point here is point A, and this point here can be point. Oh, actually, let's make it here. This point here can be point X, and let's make this point here X plus H. So think of it like X plus a little bit. In other words, the distance between X and X plus H is just H. Plus that little bit of extra space. Okay, so what we really want to be looking for is the area between A and So we want to be thinking about the areas underneath this curve a little bit. So let's particularly think of the areas between A and, say, X. So this area here, and let's come up with a symbol. Let's say that big F of x is the area between A and X. So that also means that this area here, all of the area from A all the way to, including this bit, up to X plus H, that would be, big F X plus H. That's what that would be. And if x is brought closer so that x is actually at the same spot as a, that would be f of a. And because if x is right here at a, there would be no area. So f of a must be 0 under this definition. Okay, what we're going to be investigating in particular is what is the area of this little sliver here, this bit here. What is that area going to be? Well, we can see that it's the area of this whole bit, take away this area here. In other words, the area of this little slivery bit here, let's just write it like this, area of, I'm just going to write the bit, is equal to the area of the big bit, x plus h, take away f of x. So just to say that one more time, it's the area of this whole section here, take away the area of this little bit, gives this sliver bit here. Okie dokie. Now let's find an expression for that area of that little bit. We can say that little bit, well, if it gosh, terrible mind blanks occurring. Okay, let's write down one more thing we know about that area of that little sliver. We know that it's larger than, if we take this point here and we go straight across, we know that it's larger than that area there that I've created. It's larger than that area. So that little area, well, it goes up to a height here of f of x is what that height there is. And this box is h wide, so that area is f of x multiplied by that little bit h. So this area of the bit is larger than that. So we can do this, f x plus h minus f of x. But it's also smaller, the actual area is smaller than if we start at this opposite corner, oops, here, and go backwards that way to make a larger box. Okay. So the area is actually smaller than that larger box, because hopefully you can see the function kind of cuts through the middle of those two boxes. So it is smaller than that big area, and that big area is, well, this point here, the height of it is the function of x plus h, and the width of it is h again. So this one is function of x plus h multiplied by h. Okay, so here we've got this expression now. The area we're looking for is sandwiched between these two expressions here, somewhere between those two. So what we can do is we can divide, there's a h here and an h out there, so let's divide everything by h. So we've got f of x smaller than, so if we divide that by h, but also this middle bit by h, x plus h, x, so that middle bit has to be divided by h, smaller than f of x plus h. There we go, so it's sandwiched between those two bits there. So what this means basically is that if these two things on the outside are equal to each other, then because this thing in the middle must be actually in between those, it must be equal to them as well. Okay, now the only way f of x can be the same as f of x plus h is if we take the limit as h approaches 0. Because if h is 0, then this term here becomes f of x, which is the same as this term here. That will mean that this bit in the center must be f of x as well. Okay, so what we're trying to do is we're collapsing h down. So this box here is so tiny up here that there's no difference between those two areas of those two rectangles. So in other words, we can find an expression for our area by writing this center bit. If we have the limit as h approaches 0 of f of x plus h minus f of x over h must be equal to these two sides. Okay, remember here h has been 0, so it's f of x as well. And because it's sandwiched between, it just becomes this same term. Oops, too far. Alrighty, so now you should hopefully recognize this left-hand side as a derivative. So it's actually a derivative by first principles, which means that we can say that this function f of x here actually must be the antiderivative of f of x dx. Okay, because this is a derivative, what we've done is integrated both sides. We've done a big integral of this to get back our function, and we've done a big integral of this side here, which is what we have on the right hand side. So we've basically said that our big F must actually be an antiderivative of little f. So we can also write this another way, just so you know. We can also say that that our integral of f of x dx must be f of x plus a constant. That's just writing the same thing in the other way. Okay, now let's think about what happens when x is actually equal to our point A. And you'll remember that big F of A we've already defined to be 0 earlier on when we first talked about what f of x is. We said f of a is equal to 0. So because of this, let's work this out for when when x is a. So we can say that the antiderivative of x dx is equal to f of x plus c. F of a plus c. And that has to equal 0 because it is 0 at x equals a. So from this we can say that c is equal to negative f of a. Okay, so we can now say, so let's write that back into our general form, this bit here, with our value of c. So we can now say that our integral of f of x dx is equal to f of x minus f of a. So that means if we have the two, let's put our terminals in now. If we have a and b of f of x dx. Now instead of x we have a b, f of b, take away f of a. And that is our fundamental theorem of calculus. So there we go, we have linked the algebra to the actual area of a couple of rectangles and sandwiched our function in there. So we've basically proved the fundamental theorem of calculus.